the neural network. And let's look at the two-layer neural network in order to compare. Now, the deep network, we can't really make this comparison, but for the two-layer neural network. Okay, so if you remember, there was the initial input layer. So you have X, then you have number of hidden units, M hidden units. So you have one set of weights, W1, and we call these weights, these perceptrons, V1, V2, and so on. And then we collected those into one final perceptron, which we call W. Okay, and that was the output. And inside here were tanh. Okay, so the last guy is sine. Okay, so inside here, in this activation is tanh. Okay, so what's the final hypothesis? So h of x, okay, equals, the sine of something. So let's figure that out. So this is a bit of review. So h of x is equal to the sine of, okay, so now we have a perceptron, W0 plus the sum, okay, from I equals 1 to m, or let's say I equals 1 to m, the number of hidden units in this node. The tanh, so what's coming out of this node is the tanh of what? Of a perceptron evaluated on the input x of Vi transpose x. So this is the two-layer neural network. Okay. Turns out we can simulate the two-layer neural network by choosing an appropriate kernel. Okay, so what's the kernel? Let me change the kernel. That's all I'm going to do. Change the kernel. The kernel is going to be tanh of some constant C x transpose x prime. So x dot x prime plus, let's say, some other constant nu. Okay. Now, it turns out that this is not a valid kernel for all choices of nu and c, but there are specific conditions on c and nu that we can pick in order to make this a valid kernel. And I leave you to look around in the literature for what are the valid choices of c and nu. But this is you can give me x and x prime, and I can define a kernel. Okay, it's a function of the dot product between x and x prime. Okay, modulo some constants, and then I take the tanh. Okay, so now in the RBF, I took the distance between x and x prime, and I did e to the minus of the distance squared. In the polynomial kernel, this is similar to the polynomial kernel. The polynomial kernel was k of x and x prime is equal to some constant plus x transpose x prime to power q. Okay, so that's the polynomial kernel. Okay, so this is the neural network kernel. Okay, so let's see what that final hypothesis looks like. So, in general, it's the same. It's the expansion over the support vectors. When you solve the dual quadratic program, you get the alpha n star. It's the expansion, the sign of the expansion over the support vectors of the similarity between your support vector and your test point plus the optimal B star, okay, the bias. Okay, and we can see explicitly what that would be in this case. Okay, so this would be the sine of the sum over your support vectors, alpha n star, yn, okay, the kernel, which is tanh of, some constant c x n transpose x plus some constant nu, okay, and then plus b star. Sign off that. Let's compare. Well, I still have my constant W0. I have my optimal bias B star. But now let's look at the sum. So here we have a sum over hidden nodes of the tanh of, the dot product between x and the vector v for corresponding to the perceptron into node I. And this vector v is highly tuned to the data. Okay. In fact, this is has an augmented term. So this is actually Vi transpose the unaugmented x plus Vi0. Okay. And here, well, I left out the Wi here. And here, we have exactly the same term. Okay. We have a weight for that corresponding non-zero alpha. Okay. So we have a weight times the tanh of, some vector times x, okay, plus a constant. And you can choose these constants. Okay. So this is playing the same role as Vi transpose. And this is playing the role of Wi, and this is playing the role of W0. Exactly the same functional form. Now let's see how this worked for the neural network. For the neural network, unlike the radial basis function, where we pick centers in an unsupervised way, for the neural network, we finely tune these VI. Tuned. And you can view these VIs as finely tuned feature transform. So you take your X and you feature transform it into an M-dimensional space. Okay? And M has to be fixed. Has to be given in the two-layer neural network. And in the support vector machine with the neural network kernel, this simulates the two-layer neural network. Look at what has happened. Okay. We have exactly the same functional form, but you don't get to tune the features. The features are support vectors. Okay, so the features are support vectors. The features in the first layer. So these weights in the first layer are support vectors. Very interesting. Okay. So in some sense, you're computing the similarity between your X and a support vector, but that turns out to be just the dot product, and then you take the tan H because that's the kernel, and that's what simulates the neural network. And then, okay, how many hidden nodes are in this neural network? The number of hidden nodes is equal to the number of support vectors. You don't get to choose it. You don't even need to use. So all this gets automatically set in the optimal hyperplane algorithm with this kernel. So the number of hidden nodes in your first hidden layer is the number of support vectors. That's automatically determined. And then also these weights. The feature transform is automatically determined. The feature transform that is being implemented by the first hidden layer is automatically determined, and it's very simple. It's related to the support vectors. So everything is automatically determined, and we're simulating the neural network. Wow! Look at this power. Now it turns out that the two hidden layer neural network is all you need to be able to implement anything. Okay? We use more depth in practice, but you don't need it in theory. Okay? And so what this means is that the support vector machine with the right choice of kernel can basically simulate the neural network. And so if you can see the amount of power that I've given you, you can pick whatever kernel you want as long as it's positive, definite, and symmetric. You can pick whatever kernel you want, and then you can run this optimal hyperplane algorithm in that space, usually infinite dimensional, without any worries. You just have to pick, your regularization parameter if you're doing the soft margin. Okay? And you have to pick your kernel parameters, in this case C and U. But with this power of this kernel, we can basically do anything, and we can do it efficiently. And we can do it optimally robust. Optimally robust because it has maximum regularization, maximum margin. So you can think of this as, not only have we automatically determined the number of hidden units, okay, and the transform weights, the perceptrons in the hidden layer are determined by support vectors. Not only have we determined those, but we have the optimal fit in the sense that it is the maximum margin. So you cannot get more robustness. Okay, so support vector machines or kernel machines, support vector machines with the kernel trick, which we call kernel machines, can do radial basis function networks. They can do neural networks. They are maximally regularized, and it's a quadratic programming algorithm, which is not iterative. It's a convex optimization problem. It's an example of a convex optimization problem, which we know how to solve essentially exactly. So what could be better? It's a real power tool. Okay? And so therefore it's worth taking a little bit of a closer look at what exactly is the kernel. So what exactly is the kernel?